Okay, welcome everyone to another SIP seminar for the spring semester. It's my pleasure to have Professor Konstantin Mischaikow join us today from the Department of Mathematics at Rutgers. Just as a brief introduction, Konstantin did his PhD from Wisconsin-Madison. So go Badgers, given that that's one of our common connections. But of course, it's beyond that. He's been doing wonderful work in a number of research areas, including dynamical systems, which he's going to talk about today. In terms of just brief background, he's currently a distinguished professor of mathematics at Rutgers, where he joined in 2006. He also had positions at Brown and Michigan State and Georgia Tech. And his research interests include nonlinear dynamical systems, computational dynamics, and topological data analysis. And today he's going to teach us a little bit about identifying dynamics from finite data. So with that, I'll hand it over to Konstantin, all yours. Thank you.
Thank you very much. Let me tell you a little bit about how this talk is going to go. You know, I'm a mathematician, and so I actually care about the theory more than the applications. And so the way I'm going to give the talk will be a little bit theoretical, a little bit of math lectures at the beginning. But if you're patient enough, then I'll try to show you that actually some of these ideas might have some useful applications. All right. So let me start with a rather bold claim that dynamical systems, as we've learned it for the last half century, is not, I don't think, the appropriate first tool for understanding data-driven dynamics. That's a kind of a bold claim, and what I'd like to do in this talk is to give an alternative, complementary. I want to emphasize complementary. I mean, I really care about being able to do dynamics from data, but of course, I don't want to throw away everything that we've learned over the past few centuries. So given that it's a bold claim, here's a theorem that actually, I think, justifies it. I'm not going to go into the details of it. You can look it up. Basically, what it's saying is that if we think about dynamical systems from the level of invariant sets, then we need at least uncountably many invariants, or else we won't necessarily be able to distinguish dynamical systems. So another way of saying this is the dynamical systems, as we typically study it, is an extremely complex, fine, rich subject. Maybe too rich. That would be my take. Is that if we want to work in a what I think we're doing these days, where data is handed to us, we don't have a model to work with, then the classical theory of dynamical systems is just too rich. And so what I want to do is to talk about a really dumbed down version. All right. But I want it to be a computable dumbed down version. And so with that in mind, let me start with a thought experiment. Again, very, very simple. I want to get the ideas across. And I think the best way to do that is some really simple examples, but then I want to build some machinery so that I can actually deal with interesting examples. So think that I have an ODE. I have no idea what this ODE is. Let's assume that it acts on the plane. And what I'm allowed to do is to pick a bunch of initial points and then we'll follow it forward in time for a few steps. All right. So here I've followed each of these initial points forward, I don't know, 5 or 6, maybe even 7 times. And what I see is that these initial points seem to be clustering. Some of them seem in forward time to be clustering on the left, and some of them seem in forward time to be clustering on the right. To me, a natural conclusion from just this data is that this is a system that exhibits bistability. And if I want to have a really, really simple agnostic description of bistability, I think of it as a partially ordered set. I start with an initial condition. Where am I going to end up? Well, I'll probably either end up somewhere on, well, the left, whatever that is. Whoops, why did that happen? Or I'll end up here on the right, wherever that is. And there's probably some stuff that will get stuck in the middle. This would be the separatrix. This is something that's very hard to see physically, but there should be some invariant set that acts as a separatrix. If you're kind of on the right of it, you end up over here, and if you're on the left of it, you end up over here. So this is an abstract realization of what I think we care about in terms of bistability. Okay, so this talk in some sense is a talk about how can I go from this kind of information to a description of what the global dynamics looks like. And what I think or at least when I looked at this picture and said, oh, things are heading over to the left or things are heading over to the right, conceptually, I had, well, stuff that started over here ended up inside, stuff that started over here ended up inside, and I'll give that a name. I'll say that I have a region of phase space as an attracting block if under the dynamics it gets mapped into its interior. All right. Now, are these really attracting blocks? Well, it's not so clear. In fact, what I did here was I took a simple ODE and I actually integrated and then made an error. So I actually put noise into this system. You could think of it as experimental error. So these would actually have been attracting blocks for the actual differential equation I was using, but they are not attracting blocks because of the noise. But maybe this is where a statistician could come in and say, yeah, with high probability, we should believe that this is an attracting block. All right. So attracting blocks are going to be fundamental objects that we're going to talk about, and I will eventually get back to that. But I want to build a mathematical machinery that doesn't require us to look at pictures and then draw graphs. I want a machinery that you just throw the data in, and then it comes back and tells me what the global dynamics is going to look like. So I'm going after this alternative definition of dynamics, and it's a very crude notion. I've already tried to convince you that if you go for sophisticated dynamics, then it's impossible to get enough information from your finite data sets. And so basically, I'm thinking the dynamics is all about where you're going and whether you get back to where you started or not. So, right, so you have a dynamical system like this thing on the left. Well, I'm going somewhere and it doesn't look like I'm ever going to get back to where I am. Whereas for this dynamical system, I'm going somewhere, but eventually I get back. So recurrence versus non-recurrence are fundamental concerns for me. I mean, this is really primitive, but that's something I'm going to focus on.
Can I ask a quick question? Is the time notion in there also, that how long it takes you to get there, or that's
I'm going to throw that away. I'm going to throw that away. All right. It's really very, very primitive. We can go back and put relative notions of time. This happened before that, but quantifying the actual time is that's going to be, trying to give decimal place values to time, that's going to disappear. Right?
Thank you.
All right. So I'm like I promised you, I'm going to do some math. All right. So there's going to be two pieces of math. And I would like everything that I'm doing either to be combinatorial or algebraic. Why? Because that's something that it's very easy for computers to manipulate, and to manipulate very fast. And the data comes in, we're going to have lots of data. We need to be able to process it. So the first piece of algebra that I'm going to talk about are things called lattices. All right. So a lattice, just think of it as, some set, and then there's going to be two operations, wedge and V, and then there's going to be a minimal element and there's going to be a maximal element. If you know about lattices, then you can, close your ears for the next few minutes. If you don't, the canonical example where this all starts from is set theory. So in that case, you have, a collection of sets, and you're allowed to talk about the wedge of two sets, which is just their intersection, or you're allowed to talk about the V of two sets, just the union. And in this setting, the simplest example would, the minimal element would be the empty set, and the maximal element would be the entire set that you're working with. All right. And the distributive property is De Morgan's laws, right? The intersection and as algebraic operations, intersection and union distribute. All right. Now, I'm only going to be working with finite sets. Again, I think that's okay. If we're talking about finite data, that's all I would ever have to work with. Okay, so this has been given very algebraically. For this talk, I find it very useful to think about it pictorially. So here would be an example of a lattice. You have your minimal element, empty set. I have an object X, I have an object Y. I can take the V of that object. This would say that if I took the wedge of these two objects, I would end up with the empty set. And then there's some, maximal set here. And these are the only elements that sit inside my lattice. When I give you a lattice, then I can always turn it into a partially ordered set. And the way I do it, one way to do that is to use the wedge operation. And so I'll say that U is less than V if U wedge V is equal to U. Back over here on the set theory side, use a subset of V. Well, what does that mean? That one way to think about that is if you take U intersect V, you get U back again. All right. So again, I'm introducing the language of algebra because there are cases where I need to use a different operation than intersection and union. But if you just think intersection and union for this talk, you'll be pretty safe. I told you the lattice is a partially ordered set. There's a special partial ordered subset that I care about, and this is the partially ordered set of joint irreducible elements. Here's a formal definition of what it means to be a joint irreducible element. If I look over here in the picture, then they're easily identifiable as elements that have a unique immediate predecessor. So with respect to inclusion, X, V, Y is including into one, and it's the immediate, it's the largest set that includes into one. And if I look at one, there's a unique immediate predecessor. So one is joint irreducible. X, V, Y, there's this X that's an immediate predecessor, and there's this Y that's immediate predecessor. So there's not a unique immediate predecessor. So this is not joint irreducible. So in this particular lattice, there are 3 joint irreducible elements. Okay, so I mentioned partially ordered sets. So let's start now with partially ordered sets rather than starting with lattices. So here's a partially ordered set. I would like to make a lattice out of that partially ordered set. And there's a canonical way to do that, and that is look at the lattice of downsets. So take an element in your partially ordered set, look at that element and everything that lies below it. That becomes a set. All right, so everything below A, well, there's nothing below A, so it's just the set A. There's just a set B. There's the union of them because I want it to be a lattice. And then the only thing that's kind of interesting is to take the element C and look at everything below it, and it is C, A, and B. All right, so I went for my partially ordered set and I made a lattice. And I told you about joint irreducible elements before. And if I look at the joint irreducible elements here, oh, I ended up with a poset, and this poset looks a lot like this poset. And that's not an accident. There's a fundamental theorem called Birkhoff's theorem that says that somehow the information in posets is the same as the information in these finite distributive lattices and vice versa. Okay, so why do I care about this algebra? As we will see, this operation, this object here is very useful for quickly understanding global structure. It's also very, very useful for computations. But if I want to understand fine structure, then I want to be working over here. And I will try to make that clear as we go through the talk. The fact that I can move back and forth, this theorem says that we're really talking about the same information. I don't need to worry about having lost information if I'm computing over here and I want to understand fine structure, or if I want a nice simple representation of what this fine structure might provide for me. Okay, that might look like pure algebra, but remember, here's my basic example. And let me show you that this algebra kind of codifies what I hope I conveyed to you in that first slide. So if I'm going to talk about lattices, these finite bounded distributive lattices, I need to have that maximal element. That'll be the full space, X. And I told you that I cared about these attracting blocks, that identifying these attracting blocks was kind of conceptually what told me that I was going to end up in here and I would possibly end up in here. Okay, so I've now given you the elements that I need in order to make a lattice. All right, so we're back to my example lattice that I've talked to you about. There's this set, so this is now a lattice of attracting blocks, the union of them, and X. If I look at the joint irreducible elements of this, oh, here is my bistability poset. This is now telling me from the global dynamics perspective that, gee, I can end up to the left or I can end up to the right. All right, so what I claim with this algebra is that I've codified all, my discussion of how I want to analyze this data. And because it's now been codified in algebra, I don't have to be able to see any pictures. I'm just going to have some way of identifying attracting blocks. All right. And how we do that, well, that'll depend on the problem, but we'll get to that eventually. Okay, so that was the first algebraic primer. The second thing is that I told you I'd like to understand dynamics, and this is a really, really crude way of talking about dynamics. Can I get more information? And the answer is yes. And the way you do that, or the way I propose to do that, again, from a purely combinatorial approach, or purely combinatorial with a plus a little bit of linear algebra, is through algebraic topology. Now, you don't need to be an expert in algebraic topology or even have been introduced to it to understand, hopefully to understand what I'm going to try to get across. I've put down a definition. And for those of you who know a little bit of algebraic topology, you'll recognize this definition, though it's more primitive than what is usually taught. So we have a cell complex. So this is, again, something purely combinatorial. It consists of a poset. Oh, and this should be a script X. That P should not be there. This should be a script X. So this part is a poset, and then there's two functions. And this function says, well, look at an element here and give it a dimension. A typical cell complex might be a triangulation of a space, right? So I look at a simplex and I tell you the dimension of the simplex. That's what this function would tell me. And then this incidence function tells me it's going to be an algebraic way for me to know whether how these cells are touching each other. And here's some technical conditions that need to be satisfied. But I'm going to keep things very simple. And whenever I talk about an incidence, I'm going to use calculations over Z2. So either a cell is touching or it's not. And again, I'm only care about cells whose dimension differs by 1 to care about whether it's touching or not. And this particular funny formula here is what would allow me to write down a matrix that acts as a boundary operator, something that squares to being equal to 0. So this generates a cell complex, if you know what that means. If you don't, it doesn't matter. I'll tell you that a cell complex generates homology, and what you should think of whenever I say the word homology is that I'm talking about a vector space. All right. So what I'm saying is that there's this purely combinatorial information. It can be turned into linear algebra, and the linear algebra, what I claim, is very useful. Okay, one more slide of technical stuff. And this is just so that when I make some statements later on, for those of you who are mathematically inclined, who would like to get into the weeds of this, I've told you something that's correct. The rest of you can just ignore this for the time being. And in fact, I would ignore it until you get into the weeds. So if I have an element of, this is a poset, I told you, I can always form the lattice of downsets. And if I take an element of the lattice of downsets, it turns out that that's a cell complex. So I can turn it from a combinatorial object into a linear algebra object. And that then gives me a lattice of closed subchain complexes. So this is a lattice of linear algebra. And here's the first place where this is still intersection, but this is span. All right. So I'm just doing linear algebra here. You can actually think of this as matrices acting on vector spaces. And here's one final definition. A lattice filtered cell complex is a cell complex together with a finite distributive lattice, kind of lattices we've been talking about, and a homomorphism from this lattice into this lattice of closed subchain complexes. Again, it's a technical condition. It needs to be satisfied. Ignore it unless you know something about this subject, and then this might make sense to you. Okay. I told you I want to have an alternative notion of dynamics. And so that's what I'm going to give you right now. So throw away everything you learned about dynamical systems, and I'm going to tell you a new notion of dynamics. So you start with a cell complex, right? So this is something purely combinatorial. I drew a picture here of, there's going to be two-dimensional cells, there are one-dimensional cells, there would be the vertices here, there would be zero-dimensional cells. Why did I draw a picture? Because if I draw a picture like this, then you can immediately, understand how things fit together. If you want to think about it as a subset of the plane, you can, but I would encourage you, if you're trying to, understand what I'm after, to think about the geometric realizations as late as possible. All right. If you actually want to pull information out this in an application at some point, you do need to do the geometrization. But working on the purely combinatorial level for as long as possible, I think, is very useful. So let me not look at the geometric realization. Let me just think about this as an abstract combinatorial object. And I'm going to say that a dynamic clade is a 0-1 sublattice of the top dimensional cells. So I've got these two-dimensional cells here, and I'm going to say make a sublattice out of that. With this extra technical condition. That just says I shouldn't try to pack too much information into this cell complex. And that's my definition. Now I claim I've given you enough information to understand a lot about dynamics. All right. Let me make it concrete, and you'll see what I mean. So here was this cell complex, and now I'm saying, choose a dynamic clade to consist of, well, an object that's made up of 4 of these, 8 of these top dimensional cells, and another 8 of these top dimensional cells. And let's build a lattice out of that, right? That's what this A is supposed to be. It's supposed to be a lattice made out of these objects. Well, we're back to our initial lattice, this one that I've been talking about all the time. So this is the definition. Now, out of this definition, once I've given you this lattice, we can talk about something I'm going to call a Morse graph, and that is the postset of joint irreducible elements. Right? And for each element in this postset, I'm going to say the associated Morse tile is, well, what is it? Well, for this P, it's in this, it's one of these joint irreducible elements. A joint irreducible elements has a unique immediate predecessor, so this makes sense. And so now I'm saying, look at the lattice elements that you have, take away its immediate predecessor. So for this simple example, you have M0, but there's no immediate predecessor, so its Morse tile is just M0. M1 is going to be the same, and M2 is take the whole space and take away the green cells. So that's kind of the only interesting operation that would be done here. And now I'm going to use the algebraic topology. So I gave you enough information. That's why I want to build a cell complex to start doing algebraic topology. And again, if you know some algebraic topology, fine. If not, what I'm telling you is there is some machinery that will take this information and produce a vector space. And that vector space has a lot of information. All right. So the assumption when I give you this definition here is that my dynamical system is generated by a differential equation, for instance. So in this particular example, if I did these computations, I would get a one-dimensional, for this object right here, the Conley index is a one-dimensional vector space that happens in this, be generated by the zero-dimensional simplices. This is generated by the zero-dimensional cells for this one. And the Conley index for this Morse tile is going to be generated by the one-dimensional cells. all right? But again, it's a one-dimensional object. Okay, why do I care about this? And that's because the Conley index can be used to identify and characterize dynamics. So a fundamental theorem, and this goes back to Conley, is that if you have a non-trivial Conley index, it implies the existence of a non-trivial invariant set. All right, so I'm going to, and in fact, there's lots of extensions of this result. All right, so we can use this algebraic topology to find fixed points, periodic orbits, even chaotic dynamics, talk about the global structure, and these now become theorems. All right, so if I have the right amount of information, then I can actually have theorems about the kind of dynamics that can be seen. The moral of the story is homology, this Conley index, plus you typically need a little bit more information, tells you things about dynamical systems. And now when I'm talking about dynamical systems, I'm back to the classical study of dynamical systems. So over here, I'm thinking ODEs. Over here, I'm thinking about this purely combinatorial information that I've put together somehow from this finite amount of data that's been handed to me. All right. Okay. Moral algebraic topology in the form of homology, which is really, at the end of the day, on the level that I'm using it, is just doing linear algebra and linear algebra computations, actually is going to give us information about dynamical systems, where I've never ever written down what the dynamical system is. I'm just letting the data tell me how it fits together. And the point is that if you do have a dynamic clade, and that dynamic clade is a lattice of attracting blocks, then we can interpret the global. We can determine, and these now become theorems about the global dynamics. So back to my basic example, right? We've already done all these computations. I identified what the Morse tiles would be, and I'm telling you I've computed, this is from the previous slide, I've computed the Conley indices, and then those theorems from the previous slide would tell me, oh, there must be a fixed point in here, there must be a fixed point in here, and somewhere in the complement here, there needs to be another fixed point. And if I look at the invariant set that's in the complement, a perturbation, so that's not written down here, but this is the kind of information you can pull out. So I don't know where that other invariant set is. It could be sitting over here. It's just somewhere in X, take away the stuff. But wherever it is, a perturbation in one direction will end up in M1, and a perturbation in another direction will lead me to M0. So I really do capture the actual dynamics that's taking place here, really captures everything that we would expect out of this bistability, the simple bistability Postset. There are invariant sets. This is where things will tend to go, or this is where things tend to go. There's a separatrix, and if you perturb from this separatrix, you could end up here, or you could end up here. All right, and both possibilities can be realized. And all this kind of information now becomes theorems if you accept that we have these two attracting blocks here. All right. These are theorems about differential equations. And notice I've never actually told you what the differential equation is. I don't need that information. So I think of this as a proof of concept. I hope I've given you some idea of how these mathematical tools that I've made fit together in this very trivial example. So let's try to do this for something that's a little bit more interesting. You know, are these ideas practical? It's fine to do a simple two-dimensional picture and walk away. But I'd like to do more. How practical these things are, well, this is very much a work in progress. I have talked back and forth about the Postset structure and the lattice structure. I used the lattice structure a lot to do the algebraic topology. The Postset structure, and I hinted at this before, is really important for computations. So let me kind of tell you about that, because that's kind of gives you an idea then maybe of how the dynamics gets recovered from the data. So I have some finite set, and I'm going to think of these as states of my system, right? And I'm going to talk about a combinatorial multi-valued map as being a directed graph on these states. And maybe you think of this as a state transition graph. But you know, I'm in this state here. The state gets measured, and so I don't know precisely where I am. 1 time unit later, maybe I'm back in the same state, or maybe I've gotten moved to this state, or maybe I've gotten moved to that state. I mean, and I think in the engineering literature, this is sometimes referred to as like cell-to-cell mappings, all right? So I have this combinatorial structure. I care about dynamics. And I told you, for me, dynamics is you're going somewhere and you care about whether you come back to yourself, whether it's recurrent or not. If I want to look for recurrence in a graph, a directed graph, then I think strongly connected subcomponents are the natural idea to use. And a strongly connected component is a maximal subgraph so that you can get from any one vertex to another vertex in that subgraph. And so, well, you could have trivial subgraphs, or you could have interesting subgraphs. And these interesting subgraphs, you see actually have arrows and really have recurrence in there. So once you've identified the strongly connected components, they form another graph, but now they form an acyclic directed graph. So they form a poset. And out of that poset, I am going to extract only the interesting strongly connected components, those that have at least one edge in them. All right. And I'm going to call that the Morse poset. We've already talked about Morse posets. All right. But this is a different way of accessing it.
So I had a quick question here. Like, should we think of this? I mean, is this finite set really our data samples? Is it made up of our data samples? Because
think of it as some kind of maybe a grid on which the data samples are put. I will get to this in just a moment. Okay. So I'm just telling you how I'm going to do some computation, and then I'll show you a computation. All right. And then out of that, I'm going to just extract this Morse graph. This is now a very nice, simple representation of the dynamics I extracted from this. All right, so let's try to work with some data and do this. Now, I'm a mathematician, so where do I get data from? I get data from maps, all right? I mean, I don't go out and do experiments. So let me think of a continuous map. I've done a little sleight of hand here because now I've worked to move to maps. And everything I told you up to now has really been working with flows, but I hope you'll grant me that. I would like to have a cell complex associated with this. So, here's my unit interval. Let's chop it up into, I don't know, 16 pieces or something like that. Yes, into 16 pieces. And here's a definition. I have, I didn't put the definition. I want to have an outer approximation of whatever this dynamical system is. So think of sending, for example, this cell to these 4 cells, this cell to these 4 cells, this cell to these 4 cells. So this is now a directed graph where the vertices are the top dimensional cells. All right. And if I do that, then my true function, whatever it is, lies in the interior of the state space represented by the images. All right. The theorem says that if you've done that, then the dynamic clade is a lattice of attracting blocks. And so this machinery, this algebraic topological machinery that I have, is going to work. If I go through and think about the posets, the combinatorial multi-valued map, this cell gets mapped to these 4. So really, this cell gets mapped to itself. It gets mapped to here. It gets mapped to there. Gets mapped to there. Gets mapped to there. Gets mapped to there, etc. Then if I look for the Morse poset, this is what I'm going to get. This will be my Morse graph. But I can now compute Conley indices, and this will be this cell here will have the Conley index of an unstable fixed point. This will have the Conley index of a stable fixed point. And so, with this very crude computation, I've kind of recovered the kind of dynamics that you would expect from this simple map. Okay, let's look at something. And what I want to emphasize is that this was done with a finite number of calculations. Here I used, if I was going to make a proof out of this, I would use error bounds. Now, I realize this is probably not what you think of as data, taking a function and putting it through a computer, but and that you might be more interested in looking at maybe some time series. So for me, time series would be a set of points an initial condition and where, or a point and where it gets sent to, right? So here would be, say, 5 time series. And you could ask, can I recover this kind of information if I just gave you 5 of these points, right? So I want to try to convince you, this is very, very much work in progress, but that this is not so unreasonable. So here's a much more complicated map, all right? So this is a map that comes from population biology. And here we have a fairly complicated Morse graph. Again, we see the bistability. This actually contains incredibly complicated chaotic dynamics, but it's being hidden in one region, attracting region. If I went through and computed the Conley indices, I would see that this has a Conley index of a period 3 orbit, stable period 3 orbit. This has the Conley index of an unstable period 3 orbit. You don't see 3 because it's a single cell down here. These are very, very small cells that we computed with. It's sitting here, it's the origin, it's a fixed point, and this would have the Conley index of a fixed point. So let's think about doing this, but where I only have time series, all right? So I only have 80 points in this domain. I have the 80 point, I have a point and its image, and that's what I have. And the question is, can I recover this kind of information? And the answer seems to be yes. But I'm surprised by how little time series we actually, how sparse the time series can be, and we still get the kind of answer. So what we've done here is we used a multi-output Gaussian process to generate a surrogate model. So we took these 80 points, we built a surrogate model, and then ran the machinery on that surrogate model. And this is the output. And it looks a little more complicated, but you can, in a very systematic way, match the information you get here with this Morse graph and do all the Conley index computations and things like this. So with 80 time points, we actually seem to be able to capture dynamics that is, I mean, this is the true dimension. These are theorems that this is a Morse Postset and the Conley indices are valid for this particular dynamical system. There's a lot of work to be done here, and there's a group of us here, Ying in particular, who's in the audience. This computation was done by Bogdan Batko. So we're really exploring just how useful the surrogate model method is, but our experimental work suggests that it is really pretty useful. So here you see, you just have those data points, but I've built a grid and then use a surrogate model to fill in for the data points that I don't need. I'd like to also suggest a different way, and maybe this is more closely related to what a lot of you might be working on, and that is networks. So I think of networks as the way people take data and try to organize it. I'm very much motivated by systems and synthetic biology, and so this might be a gene regulatory network. But if you've listened to talks from systems biologists, then you know that most of these edges that they've put in here are statistically generated. They do, they get a lot of data, and then they say, gee, it looks like 5 down regulates 3. So let me put an edge in there. And so the question that I'm interested in is, if I think of this as an agglomeration of data and with the ideas of how things interact, can I tell you about what kind of dynamics this network might produce? All right. So I'm going to assume that with every node, there is some quantity associated. If we're talking biology, you can think about it as a quantity of protein. And then you can ask, what's the dynamics that these values are going to take on if this is how they interact? My assumption is that if I see an arrow, one of these arrows here, then it tells me that if I increase the amount of quantity of protein 1, then I'm going to increase the rate of production of 4. All right, so this is in line with the synthetic biologists. The blunt arrows say just the opposite: increase the amount of 5, and that will decrease the rate of production of 2. So that's what I'm assuming when I see this network. And based on, again, systems biology type ideas, I'm going to assume that what can happen with the quantities that are associated with one of these nodes is they can either decay or they can be produced. So genes produce proteins and proteins decay. And so this is kind of what's happening with respect to, the edge tells me which values of X matter for the nth node. But basically I'm just going to subdivide this into a decay and a production. Let me do a very simple example for you. So here's a phase space. I've got some quantity that's produced. It's a protein, so it should be the quantity should be positive. So that's my phase space. I'm not giving you anything, so you shouldn't start asking me about specific quantities. So I'm only going to ask, is X1 increasing or decreasing? So I'm only going to care about the sign of this. The idea here is that low values of 1 lead to low rates of 1, high values of 1 lead to high rates of production of 1. What's the simplest caricature of that I could make? It would be a step function. All right, so there's this decay, and then low rate of production, higher rate of production. And this happens at some threshold that keeps track of down here, there's low production, and here is high production. No, I'm not. I think that there's a differential equation that is a valid model, but I do not think that this is the right differential equation. All right, I'm just trying to organize how the dynamics can occur for a network like this. All right, so this is a caricature of the dynamics. I need to build a cell complex if I'm going to use the kind of machinery I've talked about. So I'm just going to put in a couple of hash marks here around this threshold. Why? Well, that's so that I have a big enough cell complex so that I can get that homomorphism, lattice homomorphism, that technical condition I said. I want to understand how to build a multi-valued map on this object. Well, if I go down to 0 for a model like this, well, you should have the option to produce. If you go out to infinity, because of the decay rate and finite production levels, you will decrease. So I'll carry these arrows around. And notice that what I'm going to put, what arrows can go in here are going to depend on the relative values of the gammas, the L's, the deltas, and the thetas. And at theta, just at this value here and at this value here, it's going to depend on the relative values of the parameters. And you can check that these are kind of the 3 relative values that matter if you care about checking the sign of this. And so with these decompositions of parameter space, those are the arrows that I can put down, right? That's just checking for inequality. Is this quantity positive or negative for these values of theta? And in there, it seems natural to me to say, well, if this cell is going to get mapped to this cell, the arrows point here, so this cell should get mapped to here. Here I have 2 arrows pointing in, so it should map to itself. And I can go in and do the rest over here. Now I've got my combinatorial multivariate map. I can run my Postset algorithm on it. I can get the Morse graph representation, and I could, in this case, do the Conley theory and conclude there had to be a fixed point here. There had to be 2 fixed points. So we have the fixed points and the bistability. So 3 fixed points and a fixed point here. All right. Okay, what do I really care about at the end of the day? I care about this information. You gave me the network. Here's a decomposition of parameter space. And now I'm giving you a statement about the dynamics and some finer information about the dynamics. Is this at all useful? Well, if I took this as my differential equation, so here, I guess I'm choosing gamma to be 1, and I'm choosing theta to be equal to 1, L is equal to 0, and delta is equal to 4. That puts me in this region. I might expect to see this kind of dynamics. And if I look at the phase portrait, yes, that's what I see. Notice this is very far from a step function. Now, if I wrote down any combination of parameters that fit in here for this particular nonlinearity, would I get the right answer? No, obviously not. I mean, this inequality came from this step function threshold. But our numerical experiments suggest that this gives a very good indicator that if you care about bistability, you should look at this region of parameter space, not that region of parameter space. And the probability of finding bistability is much higher here than it is here. Okay, so let's use this. Let's make a switch. All right, so I claim that this actually gives a nice hysteretic switch. Here's the different parameter regions. Here's the Morse graphs that you have. Over this region, you have this fixed point. Over this region of parameter space, you have these fixed points. There's this unstable fixed point that exists over this region. That's, to me, the simplest way to fit that in. And if I now use gamma as a parameter, then you're engineers, not me. So this looks like a really robust switch to me, right? And there's not going to be any chatter. You get a very nice hysteresis curve here. All right, so this is a very simple combinatorial way to go and look for switches. So let's do that for this model. I'm going to look at an output. This will be my output node that I'll look at, that quantity. I'll put an input as a source here. Now, in this case, rather than adjusting gamma, what I'll do is I'll just think that S increases maybe the production of 0. The parameter graph, okay, so I'd have to go into a lot more detail. The parameter graph actually turns out to be a product of parameter graphs that you look at each node. So to understand the dynamics of this, I look at the parameter graph at 0. Here's a cartoon version of it. I can think of this as what happens when S is very small, and this is what happens when S is very large. And to get from S small to large, I have to find a path through this graph. This product is some product of graphs over here. What I'm going to do is I'm going to pick a parameter region in this product here, and now I'll walk with a path across here. And I can ask, do I see hysteresis like I saw before? Monostability, bistability, monostability. And if the answer is yes, great. And if the answer is no, well, ignore it. But I can talk about a fraction of the number of hysteresis paths over the total number of paths. And if I do this over every possible path and every possible parameter region here, then I can get a score of, how robust the switch is. This is, if you look at all, well, we didn't do quite all 20,000 3-node networks. We only did about 14,000 of them. But what you see is that if you want to have a reasonable switch, then there's only about 1% of the networks that might act as a switch. And there's a handful up here that actually seem to work pretty well as a switch. Right here, we're looking at this particular network. I mean, I literally have done almost all three node switches. So I look at this one, here's that switch. If I'm doing biology, this is not such a good design, because if I lose one of these edges, and biology is very noisy, so there's no reason to believe that edge is necessarily there. If I lose this edge, then this will not act as a switch anymore. So what I'm going to do is I'm going to redo this computation and look at this hysteresis score where I allow for dropping out a single edge. And if I look at these top 14 examples here, then I can look at how robust something is if I drop out an edge. Not surprisingly, this guy is not very robust if I drop that edge. But there are some of these networks that are robust even up to losing edges. So here are the top 14 networks, and the ones that are in black are the ones that are, or the dark dashed are the ones that are robust with respect to losing edges. And these are the kind that are consistent in the sense that here, this is not so nice because this node is supposed to be an activator and a repressor. That's hard to do in biology. This seems to be much more easily designed biologically. And Enoch Young at UCSB is actually trying to make this in E. coli. All right. And so this is a joint project with groups at Duke and Montana State. So we're actually giving potential designs for synthetic networks. I'm running late, so I won't run through. I'll just flash slides up for looking for oscillation rather than switches. All right, so this is a cancer network where they care about oscillations. We've built software so you just throw the network in, you build a database that has all these Morse graphs, knows the parameter regions. I want to emphasize this is extremely fast to compute. This is a 29-dimensional problem. The software divides the parameter space up into about 800,000 regions. For each region, you compute the dynamics, but this is fast. So it takes about a half a minute to do the entire computation. Once you have done and this is all 800,000 regions. So now you can ask, is it possible that this thing produces oscillations? And the answer is yes. There's about 7,000 of these regions where you do have oscillations. If you plug it into an ODE and do a simulation, well, oftentimes you end up with the kind of oscillation that is measured biologically. So this does seem to be a very fast way to go and check dynamics here. We're in the process right now of doing a lot of extensions. There's no reason why these edges should be modeled by a single threshold. We can have multiple thresholds in here. We can have non-monotone interactions. We can have more complicated controls associated with, say, phosphorylation or ubiquination. I think there's a lot of room if you came to me and said, here's kind of network and here's the type of control here, for us to see if we could model that in our current framework or our very near future framework. We're doing network and circuit design. We're working on the algebraic topology so that we actually get theorems out of this. Identification with specific ODEs is a very hard problem because, I mean, this is a 29-dimensional parameter space. You pick a set of ODEs and try to understand the dynamics over a 29-dimensional parameter space. That is really hard, but we're making some progress here. And like I said, we're really trying to take this theory and push it into different directions. With Postdoc here, William Coelho, we're trying to move it into the ecology sphere. But I would be very interested to, if any of you have ideas in other areas where kind of understanding networks and their dynamics would be of use. So I will stop there and just re-emphasize that this is very, very much work with a lot of people. Thanks.
Thank you so much, Konstantin. We'll have a virtual round of applause for the wonderful talk. So are there any questions at this stage? We have a few minutes where questions could be asked. So I had a question regarding the discretization that you discussed. Is that like in the software that you discussed, it said that it divided the 29-dimensional space into 800,000 or some regions. Is there like a sort of like a rule of thumb that you just do discretization along these lines, or is it not going to depend upon the number of data samples that you have, that based upon that you sort of like, make it more crude or more finer discretization?
So for this software, where we're starting with the network as input, there, when you go to this node and you look at how many in edges there are and how many out edges there are, and you have to decide kind of the algebra of how you want to take the input information. The software then already knows how to subdivide parameter space.
Okay.
And that's a question of computation. That's an algebraic geometry question. All right. That's actually very hard, but we've done this for basically up to 5 input edges. All right. Number of output doesn't matter. It just grows extremely fast if you don't give me any constraints. But up to 5 inputs, we pretty much know what's going on.
So you use basically like mathematical machinery to come up with that number, and it wasn't just arbitrarily thrown around. Right. Let's divide it into 800,000 regions. Right,
exactly.
Okay.
Now back here where we're working with let me get out of this for a second. Can I? Yes. Back here where we're really working with where I want to be working with data, right? Right. I mean, I'm doing it with numerics so that I can generate data and know what I'm supposed to get as an answer, right?
Right.
Here, what we did was we actually took this, and I don't know whether we used 2 to the 20th or 2 to the 30th subdivisions, right, of this region. Here, there's a lot of room, I think, for choosing alternative subdivisions on which to use your surrogate model.
I see.
All right.
And does the computational complexity comment that you made for the network problem, does that hold in here also? Would it stay like, how is the computational complexity of these kinds of problems?
This is much more expensive because of the way we're subdividing phase space.
Right.
But that is, okay, so let me make a claim that I can't substantiate other than wishful thinking. But if you think about what people in machine learning are doing, all right, they're working with 100 million parameters. And basically, once their machine has been trained, there's a spline. If it's been using a ReLU learning process, it's basically taken this 100 million dimensional space and it has a spline approximation, right? It's done a spline decomposition. And that spline decomposition then tells it, whether it's you're looking at an ostrich or an orange, right? The fact that they can do that using splines tells me that we should be able to do something similar here. We have to get rid of our cubical decompositions. I mean, that was easy for me to work with. But if we figured out how to do the spline decompositions here, I don't see any reason why we couldn't be doing that same kind of work here that the machine learning people are doing.
Sounds good.
It sounds good. And I even, so if there are people who think about that, I would love to talk to them about this, because it's not something I understand, but on the gut feel, I don't need, that's why the cell complex is something purely combinatorial. I don't need a geometric realization in order to work with it, right? That's why I'm so emphatic about do the combinatorics and only at the very end think about the geometric realization.
Great. And thank you. So if anyone has, we are right at the top of the hour. If anyone has like a quick comment, we can take. Otherwise, I guess clock turned 3:01. Anyone has any further questions?
Hey, Wahid, I found this talk fascinating. I just want to ask, is there like a tutorial that can kind of get us started if we're interested in learning a little more for people who aren't actually in the field?
Yeah.
Is there anything approachable?
So I gave a series of lectures, so 3 lectures. I mean, they were addressed to a little bit more mathematical audience last week at KTH, and those lectures are online. And then there's a bunch of references associated with that. But I am here at Rutgers, so if you want to chat, I am more than willing.
In the old days that would matter, but it's sort of like, I'm not actually allowed on campus.
Neither am I, but we can Zoom, and then, when life gets back to normal, we can pick up on those.
Okay, maybe we could start. If you did 3 lectures, maybe even if it's more mathematical, some of it's a little slower to start. That maybe that's a starting point. The thing is, I have some problems I'm working on where I think, I think the math you described is really what's going on, maybe. But I don't exactly want to waste your time. Without sort of having a few more clues beforehand. Does that make sense?
Okay, so let me say, it's also, I don't want you to waste your time going down the wrong road, right? And I think a discussion might, if there is something to this, then I definitely want to discuss with you. And if there isn't, then I'd like to save you as much time for you as possible. I can give the links to the KTH lectures, and then we could have a chat.
That sounds great. Thank you.
So what's the best way to get the KTH?
I think, Konstantin, if you can send them over to Joe, and he would just share it with the entire mailing list.
Okay.
Okay.
That'd be great.
Yeah. So with this, I would like to thank Konstantin again for the wonderful talk and another virtual round of applause. And
Hey.
thank you so much. And we will resume in 2 weeks with the talk by Ji Gao from our CS department. So till then, stay safe, everyone.